we will do one small analysis and we will observe one small point, okay, from a small experiment. Let me take a board like this, a cardboard like this, and what I'm going to do is I am going to see it's a cardboard and I am placing it in some inclined manner, okay. So I am placing a cardboard in an inclined manner. What I am going to do is I am having two drops here, one drop of water and one drop of oil. So I am going to place one drop of water here at the top of the cardboard and one drop of the oil on the top of the cardboard. So I am going to place one drop here and one drop here. So I am placing it one drop and I am placing this in an inclined manner, okay. So it was in inclined manner. So it is inclined like this, it is somewhat inclined like this, and I am placing one drop here and one drop here. So what will happen, I am placing one drop of oil, one drop of water, and I am allowing it to flow at the same time. That is, I am removing my hand, and I am allowing it to flow at the same time. So which one will reach the base? Which one will reach the base faster? So one drop of oil, one drop of water, both are allowed to flow at the same time. Okay. So obviously we clearly know this, water is going to reach the base faster compared to oil, right? So water is going to reach first if I compare with oil. So indirectly, if you observe about the density of water and oil, they are almost same. So water is approximately equal to 1000, and similarly oil's density is also approximately 1000 only, not exactly 1000 but approximately, both of them are 1000. So even though densities of both oil and water are same, but why water is reaching the base first and why not the oil is reaching first? So when the fluid starts to flow, initially when the fluid was at rest, their thickness or something, their density can be measured, and clearly we can distinguish between oil and water. But when the fluid starts to flow, even though both of them are having same density, I cannot say that both will reach the base at the same point, right? So when it is flowing, there should be something else which we need to be analyzed properly, or which we need to understand properly, and that is what its flow behavior. How, when a fluid starts to flow, what is its behavior, right? So flow behavior of that particular fluid can be analyzed by understanding this small property called as viscosity. So viscosity clearly indicates the flow behavior of that particular fluid, either it is oil or water or mercury or whatever it is. If I want to analyze the behavior of the flow, the fluid is flowing, if I want to understand that, then I need to study viscosity. And what is this viscosity? We will see one by one through some explanation. See, let us take a solid surface. A solid surface is here. Okay, a solid surface is here, and I am allowing a fluid, any fluid, don't restrict to this is what my fluid or that is what my fluid, any fluid is going to flow over the surface. Any fluid is going to flow over the surface. So this is the fluid which is flowing. Okay, so any fluid I can take. Now there is something called as no slip condition. Something we have to know about no slip condition. No slip condition, from the name it is very clearly known that there is not going to be any slip. There is no slip of the fluid. So what does it mean? The interface, this is solid and this is fluid. So interface between fluid and solid, if I take all the fluid molecules, so if I take fluid molecules which present at the interface of this particular solid and the fluid which is flowing, let us assume that the fluid is flowing with a velocity v, okay, and the solid is stationary. For now, let us assume that the solid is at rest, okay. Now by no slip condition, what I could say, this fluid will flow over the solid at a velocity v only, but the fluid molecules which are exactly near to the solid, okay, the fluid molecule which are exactly near to the solid are nothing but exactly at the intersection of solid and the fluid, all this fluid molecule will have zero relative velocity. So let me write it here, then I will explain it. So all the fluid molecules at interface, okay, interface is what? Interface between this fluid and the solid. So fluid molecules at the interface between the fluid and the solid is going to have, it's going to have no or zero relative velocity between fluid and solid. So let me explain. The relative velocity between these fluid molecules which are near to the solid will be zero, or in other sense, this fluid molecule will reach the same velocity as that of solid. Okay, to say it in a very simple manner, all the fluid molecules are going to stick, with the solid itself. So if I want to say in a simple, fluids stick on solid body itself. So it is something like the fluid molecules which are near to the solid will stick on the solid surface itself. So if this fluid stick on the solid surface itself, then whatever the velocity at which this solid is moving, same only this fluid molecule will also move. Total fluid is flowing at velocity v, that is different. I'm sending the fluid at a velocity v, that is different. But the fluid molecules which are near to the solid surface are reaching to a velocity which is equal to this solid velocity itself. In this case, the solid is at rest. Okay, so this complete fluid molecules will also reach rest only. If suppose the solid is moving, let us assume that the total fluid is moving at 10 meters per second, and the solid is also moving. The solid is also moving at some 5 meters per second. So what will happen is, this fluids, when it is touching this solid, the totally it is going to move at 10 meters per second. But exactly at the interface, due to no slip condition, this fluid molecule is going to stick with the solid. So it is going to stick with the solid and it is going to reach the same velocity. So this fluid molecule will also have the velocity of 5 meters per second. Okay, so that is what no slip condition is. And what does it mean by no relative velocity? Relative means with respect to one another. So I am finding velocity of this fluid molecule with respect to solid. So velocity of this fluid molecule with respect to solid is zero only, right? There is no relative velocity. For example, I will give you some basic example. Some basic example from our mechanics. Okay, a person is sitting. Okay, a person is sitting in the bus and the bus is moving at 100 meters per second. Just for an example, a bus is moving at 100 meters per second. A person is standing in the bus stop. A person is standing in the platform, he is standing in the bus stop, and let us take this person is A and this person is B and bus is bus only. Okay. Now there is another person who is sitting just opposite to him. So let us take the person is C. Okay. Now let us have two observers. One observer is C and another observer is A. Okay. For C who is sitting inside the bus only. For C, the velocity of B will be what? Velocity of the person B will be 0, right? Because he is also sitting, he is also sitting. So velocity of B, if C observes, the velocity of B will be 0 only. Because both of them are rest with respect to bus, because both of them are inside the bus. So both of them are at rest only. So if C observes, B will be at rest only. Now come for this next observer. If A observes, total bus is moving at 100 meters per second and B is inside bus. So B is also going to move at 100 meters per second. Okay. So there are two observers, one is C and one is A. So if C observes B, he is going to be at rest only because he is also inside bus. Both of them are inside bus. So both of them will be at rest. Okay. It is very common phenomena, you can observe it. A person is sitting near to you in a bus. For you, you will imagine that he is at rest only. He is not walking or he is not moving. But for some other person who is outside the bus, if he sees a person inside the bus, he will be observing that that person is moving at the same velocity as that of the bus itself. Now this is what we will call it as relative velocity. For this person, he is finding the velocity of person B with respect to bus itself, right? So velocity of person B with respect to bus is 0 only. With respect to bus, B is not moving, right? So it is 0 only. But for this person, when he sees velocity of B with respect to earth, right? With respect to earth or with respect to the person A. With respect to earth, the velocity of person B will be 100 meter per second, right? So velocity of B with respect to bus itself, that is inside the bus itself. I am considering bus itself my reference. If I consider bus as my reference, the velocity of B is 0. So relative velocity of B with respect to bus was 0 only, because both of them are moving at same velocities. Now velocity of this particular person B with respect to earth will be 100, because both this person B and the bus combinedly moving at a velocity of 100. Okay, so this is the concept of relative velocity. Here I am finding relative velocity of B with respect to bus. Here I am finding relative velocity of B with respect to earth. Now take the same concept from bus and the person and apply it in solid and fluid. So these fluids are something like the person who is sitting inside the bus, and this solid is the bus. So if this solid is moving at 5 meter per second, and if this fluid stick with the solid, that fluid will also move at 5 meter per second only. So the relative velocity between this fluid and the solid is 0, right? There won't be any relative velocity between this fluid and the solid. Okay, so that is what no slip condition is. So no slip condition is nothing but the condition such that the fluid molecules which are at the interface of the solid body will be having no relative velocity, or simply the fluid molecule will stick with that particular solid itself. Let us take an example. Like there was a solid surface here. A solid surface is there, and let us consider it is at rest. And now the fluid is flowing in this direction. Any fluid, maybe gas or maybe it is a liquid, whatever it is, a fluid is flowing in this direction. And I know, or everyone knows, that the fluid and the solid interface, it's exactly at the interface. It will be at rest, or there won't be any motion of that. So here it will be no slip condition. So the velocity of that particular fluid will be 0. Already we discussed about a concept of cohesion, right? So between two fluid molecules, there will be force of attraction. It is something like this: the two fluid molecules are attracted. There will be something, if you imagine this, each fluid molecule like a person. You are imagining each fluid molecule as a person. It is something like each person is holding their hands. They are tying their hands. One hand of this person is tied with another hand of another person. Similarly, this person's hand is tied with another person. Same way, each molecule has been tied with each other. So this tie, or this thread by which I am tying the two hands, are nothing but the coercive forces. So there will be always a coercive force between the two molecules. So now see here, until it reaches this point, all the fluid molecules here will be having coercive forces, that is, they will be tied with each other. Once it reaches this point, the fluid molecules which are present at the interface, suddenly reaching 0 velocity. Suddenly it is reaching to rest, right? So suddenly it is reaching to rest means the fluid molecule which are attached with this fluid. For example, I am considering a fluid which is exactly near to this, okay? And this fluid molecule will be attached, right? This fluid molecule is attached to the fluid molecule which is at rest now. But still I am sending the total fluid, bulk of the fluid at some particular velocity. You will take the velocity to be v. So this fluid molecule which is attached to this fluid molecule will also try to move in the forward direction with a velocity v. But what happens? These two are tied with each other. So one person is holding, that is the bottom person is holding to some point, and he is holding another person, another hand is tied to this person. So one hand of this person was holding something very tightly, and this hand was tied to this hand, and this person is not trying to move, but this person is trying to move, but still he will stop, right? He cannot move for the longer distance, he cannot move with the same capacity. If suppose with the velocity v, if you could cover some 2 meters or something, now since due to this tie or due to the coercive force between two molecules, this fluid particle cannot move for the same distance, okay? So now what happens is, if suppose generally if he moves with a velocity v, he covers this much distance, but now due to the coercive force, this molecule cannot move the total distance. So it can move only for some distance which is less. Let us assume that it is moved only to this distance. So this fluid particle has moved to this point. Now again there will be another attachment, right? There will be another attachment, there will be another molecule. Now similar case only, this fluid molecule will try to move with the velocity v, but there was attachment between these two molecules because of the coercive forces, and this molecule is retarded. What actually happening? This fluid is trying to move at a velocity v, but it is getting retarded, that is it is getting pulled back due to this fluid molecule, because this becomes 0. So due to the total velocity of the fluid molecule which is near to the solid becomes 0, this fluid molecule which is near to this solid molecule, or the fluid molecule which is near to the fluid molecule which is at rest, is also getting retarded, that is it is getting pulled back. Similarly, this fluid molecule also cannot move for the total distance v, okay? If total distance is this, it cannot cover the total distance v, it will cover only, let us take, it is covering only this much distance, okay? So it is covering only this much, it is covering only this much distance. Now what happens again there was another fluid molecule, and again there was another coercive forces, and similar case occur. This fluid molecule will try to move to the distance, for example it tries to move to this total distance if it moves with a velocity v, but due to the attachment, due to this fluid molecule cannot move freely, it will retard back and it will move only to some distance, and this is, and let us keep this is what the distance it reached. Similarly, what happens to the another fluid molecule? Same way, there will be attachment, there will be coercive forces, and this fluid molecule cannot cover the total distance, it will cover only some distance, and let us take that molecule is that point, the covered is this. Similarly, after some particular point, the effect of this fluid molecule won't be there. So here if you compare, you can easily observe this. Initially it is not at all moving, it is moving some distance, it is moving distance which is more than this, and this fluid is moving distance which is more than this, and this fluid is moving for a distance which is more than this. Similarly, the distance will be keep on increasing, and at one point the fluid molecule will move at the same velocity v, so it can cover the same distance, okay? So now what is happening here? This profile which I got, right? So I got a profile here, this profile is keep on increasing, that is initially 0 velocity, velocity increased a little, velocity increased a bit, velocity increased a bit, velocity increased a bit. As it keeps on increasing, it will reach the same velocity v itself, okay? So now what is happening, if I consider this is y, the velocity is function of, velocity is varying with respect to y itself. If I take y is equal to 0, that is exactly at the interface, if y becomes 0, velocity is becoming 0 itself. At some particular distance y, if I keep on increasing the distance and some particular distance y, this velocity is reaching the same velocity with which it started to flow, okay? And this profile which I got is called as velocity profile. And now see, I drawn this profile only for a single fluid molecule, but this will happen for all the fluid molecule, right? Even for the fluid molecule here, for the fluid molecule, all the fluid molecules will be having coercive forces, all the fluid molecule will be having coercive forces, and similarly all the top also will be having coercive forces. So what happens? All the fluid layer, this complete fluid layer is going to get retarded by this fluid layer, and this complete fluid layer is going to get retarded by this fluid layer, and this complete fluid layer is going to retarded by this complete fluid layer. The same way each fluid layer is going to get retardation by the fluid layer which is below it, right? So all the below fluid layer is going to offer a resistance against the top fluid layer, and that resistance between these two fluid layers, or between these two fluid layer, or between these two fluid layer, or between these two fluid layer, the resistance which is offered by one fluid layer over the other fluid layer is called as viscosity. See, viscosity is nothing but a resistance which is offered by one fluid layer over the other fluid layer, and it is caused due to the coercive forces, right? And the resistance, again here there will be resistance because this fluid layer is going to resist the motion of this fluid layer, and this fluid layer is going to resist the motion of this, and this is going to resist the motion of this, and that resistance, that internal resistance between two fluid layers are called as viscosity. Okay, so now I guess you would have understood what is viscosity. Viscosity is simply resistance of one fluid layer offered by another fluid layer. Okay, offered on another fluid layer. To say in a very simple manner, it is a resistance between two fluid layers. How it is caused? It is started due to no slip condition, and I am going to get a velocity profile. If there was a viscosity, I will be having a velocity profile. What does it mean by velocity profile? The velocity, initially the velocity was u1, u2, u3, u4. As y keep on increases, when y is equal to 0, velocity is 0. As y keep on increases, velocities keep on increasing, and it is reaching to the original velocity itself. And this profile which I am getting, which I am drawing due to this variation in velocity is called as velocity profile. So here we discussed about viscosity qualitatively, that is what is viscosity, we discussed about that. Now how to find viscosity mathematically, we will see that, okay, or what is the equations related to viscosity. See, a solid object and there was a velocity profile, it developed an velocity profile. When a fluid flows or the solid object, there will be development of velocity profile. And here the velocity is going to become 0, and here the velocity will be increasing, so velocity is a function of y. Now what I am going to do is, I am considering at a distance, any distance y, the velocity of that particular layer is u, small u. And for a small change in the distance from y, the small change was dy, and for this small change in the distance dy, the velocity is increased from u to u plus du. Okay, so velocity is u here, and the velocity is increased from u to u plus du. Initially it is u. For a small change in the distance dy, the velocity is increased to u plus dy. Let me take this only, that is this only. Let us consider OA, BC. Only OA, BC into our analysis. So if I consider like that, this distance is dy, right? And here the velocity is u plus du. Here the velocity is u only. See, here I drawn it as a curve. Between C and B it was a curve. But here I drawn a straight line only. What is the reason? Because this dy is becoming very small. If this dy was very small, this curve can be approximated as straight line itself. Okay, so this dy is small, so this curve will be straight line itself. Okay, it's approximately, it is a straight line. Now if I want to represent this velocity in terms of length, okay, so for a small time I am taking, for a small time dt, I am considering for a small time dt, the velocity from this point to this point was u. If I want to convert it in terms of a distance, it will be u into dt, because I know that velocity is equal to displacement by time. So displacement will be equal to velocity into time. Now for a small distance, for a small time dt, velocity was u, so u into dt will be the displacement. So the displacement was u into dt. And what about this distance? The velocity is u plus du and the time is dt, so this distance was du into, this is the total distance. Now let me draw a straight line like this. If I draw a straight line like this total distance is u plus dt. So what will be this distance? That distance should also be u plus dt, u into dt only. So similarly, this distance is u dt, so this distance is also u dt. Then what will be this distance? This distance will be nothing but u plus du dt is the total, u plus du dt is the total distance minus u dt, minus u dt. So this and this will get cancelled, so du into dt. So this distance was du into dt. Let us take let us take this small change in the angle, to be d theta. Now apply tan for this triangle. Let us take this is O A B. So if I apply tan theta for that, tan value for that triangle, tan d theta will be equal to, opposite is AB by adjacent is OA, which is equal to, AB is what? Du into dt by OA is nothing but dy. Now we are going to deal with smaller angle approximation. Since this dy is very small, this dt should also be very small. So since for a smaller angle approximation, I can write tan theta, which is approximately equal to theta. For this, I had already discussed these types of things in our basics mathematics video. You can just go back and check the basic mathematics video. So by smaller angle approximation, I can write this d theta, tan d theta as d theta itself, which is equal to du dt by dy. Now let me rearrange this. So d theta by dt is equal to du by dy. So this is my equation which I got. Now we have to discuss few points. What is this d theta by dt? We already discussed this in the first class of our fluid mechanics when I'm introducing fluid. This d theta by dt is nothing but what? It is rate of shear strain or rate of angular deformation. That is with respect to time how this angular deformation is happening, or with respect to time how the shear strain is changing. So d theta by dt. So d theta by dt is nothing but rate of shear strain or rate of angular deformation. Okay. Now come for du by dy. What is du by dy? Du by dy is representing how velocity is changing with respect to y. So velocity, I know that velocity is changing with respect to y. So first derivative of this velocity is du by dy, and that we will call it as du by dy is velocity gradient. Okay, velocity gradient. Here it is rate. See, I am finding change in shear strain with respect to time, so I am using rate. Change in angular deformation with respect to time, so I am using rate. Here change in velocity with respect to y. Y is what? Space, right? Space quantity. X, y, z are space quantity. So velocity with respect to space, so it is velocity gradient. And if I find anything with respect to space, I will call it as gradient, and if I find anything with respect to time, I will call it as rate. So from this derivation, I found that velocity gradient is equal to rate of change of angular strain or rate of change of shear strain or angular deformation. So as per Newton's law of viscosity, the shear stress which is applied on the fluid or which is caused on the fluid is directly proportional to rate of shear strain. So how shear strain is varying with respect to time. So tau is directly proportional to rate of shear strain, where tau is the shear stress. So if suppose the fluid was like this and I am applying a shear stress like this, then the drag force or the shear force which I want to find from this will be equal to tau into area, right? Because tau is equal to force by area. So what area I need to take? For example, this is the top surface of the fluid. This is the top surface of the fluid. And I am applying shear stress on the top surface of the fluid. Then this area will be this total area, and shear stress which is applied on the fluid is tau. So shear stress which is applied on the surface of the fluid is tau, and the drag force will be this shear stress which is applied into this total surface area. Now from this, that is tau is directly proportional to d theta by dt, I can write this equation. If I want to remove this proportionality sign, I can add a constant of proportionality to this and multiply it with d theta by dt. I already know that d theta by dt is what? From the just before this we did a derivation. D theta by dt is nothing but du by dy, where du by dy is nothing but velocity gradient. D theta by dt is nothing but rate of shear strain, and this mu is constant of proportionality, which has been added to remove this proportionality sign. This mu is nothing but viscosity, and there are many names for this viscosity. For this mu there are many names: viscosity or dynamic viscosity or absolute viscosity, or it's also coefficient of viscosity. There are 4 names. Simply we will call it as viscosity or dynamic viscosity or absolute viscosity, or it is coefficient of viscosity. So that is what tau is. Now what is this Newton's law of viscosity? And this Newton's law of viscosity which I given here, there are some condition. It is applicable only to Newtonian fluids. So what is Newtonian fluids? Newtonian fluids are nothing but fluids which when it is flowing, it's going to follow Newton's law of viscosity. The fluids which is going to follow Newton's law of viscosity, we will call it as Newtonian fluid. And some of the examples are all the common examples: water, kerosene, oil, etc. Almost all the gasoline items which we are using will fall under Newtonian fluid only. Mercury, everything will fall under Newtonian fluid only. And in general, in GATE, most of the cases we will discuss about Newtonian fluid only. There are some other types of fluid, but they are not mostly used. But this is what most thing which we are going to use. So for a Newtonian fluid, if I want to find shear stress, it is equal to mu into rate of shear strain or mu into velocity gradient. Mostly we will use this formula, tau equal to mu into du by dy. This is what mostly we will use it in almost all the problems. So we got from Newton's law of viscosity, I got tau is equal to mu into du by dy, or du by dy can also be written as d theta by dt. If I want to find graph, if I want to draw graph between this tau and this du by dy, that is taking du by dy in x-axis and tau in y-axis, I can easily frame an equation from this. This is we know that y is equal to mx plus c, right? Here c is not there, that is y intercept is not there from our straight line equation. So y is corresponding to tau and x is corresponding to du by dy. If I take y in if I take tau in y-axis and du by dy in x-axis, then this viscosity is representing the slope of that particular line. So slope which is equal to m, which is equal to viscosity. And I know that for a straight line, slope value is constant. It is not going to vary with respect to the space, or the slope value will be constant. You just go back and refer to the video which I discussed clearly about slopes. So if it is a straight line, slope value will be constant. Now I can, for example, if I want to draw the curve between tau and du by dy, the curve will be like this, and this represents the curve, that is what the curve of Newtonian's fluid, and this slope of this particular line will be representing viscosity. Generally viscosity of liquids will be greater than viscosity of gases. The reason is very simple, because in case of gases, the molecules are very free, they are far away from each other, they won't be near to each other. If they are far away from each other, the resistance against the flow or resistance between two layers will be comparatively lesser if I compare with liquid. Compared to liquid, the gaseous viscosity will be very lesser because the molecules are placed at a far away places. Okay, so the molecules are distributed far away, so gaseous viscosity will be lesser than liquid viscosity. So if I take some example, and if I want to plot the graph, for example, this is one and this and this. So slope of each represents its viscosity only, and if I compare air, water and oil, this is for air where the slope is less, right? Slope is nothing but the verticalness. Go back and refer to the video which we discussed. So verticalness is less here, verticalness is more, verticalness is furthermore. So here this corresponds to air, this corresponds to water, and this corresponds to oil or oil type liquid. So here viscosity is increases from here. Air is less, water is more, and further oil is very high. So because the slope increases. Okay, slope is less here, slope is more here, slope is further more here. Okay, so that is what the concept of Newtonian's law and viscosity. Now we will do a small analysis to compare this Newton's law with a well-known famous law which we already know in strength of materials. In case of solids, the very well famous law is Hooke's law, right? And here it is Newton's law of viscosity. Newton's law of viscosity. Hooke's law states that stress is proportional to strain and shear stress is proportional to shear strain, and here tau is proportional, that is shear stress is proportional to rate of shear strain. In the first definition of fluid itself, we compared the difference between fluids and solids, where I said in case of solid shear strain is important and in case of fluid rate of shear strain is important. Shear strain is nothing but the change in the angle. Here change in the angle with respect to time is important. Okay. Now for removing this proportionality sign, what I did, for removing this proportionality type, first case I added E, and in the second case I added G. E is nothing but Young's modulus and G is nothing but rigidity modulus or shear modulus. Here tau has been added with mu d theta by dt. Now observe the meaning of E, G and mu. All of them are going to give you the same meaning. That is very important. See, that is very interesting thing. E is nothing but he represents the resistance against this deformation. This is again the linear deformation. If E is very high, then strain will be less or the linear deformation will be less. Similarly, rigidity modulus represents the deformation against the shear strain. If G is very high, then the angular change will be less. Similarly, this mu represents resistance against the rate of shear strain itself, right? That is what mu is. If mu is more, then internal resistance will be very more, it will be very high. So shear strain comparatively will be less. So all this constant value, constant of proportionality value, which I am adding in both the cases of strength of materials and in case of fluids, they are representing the resistance against deformation only. In this case, it is rate of angular deformation. In this both the cases, they are just a deformation. Here linear deformation, in this case it is angular deformation.